thank you for the great introduction. So this is my honor to be the first speaker in this seminar series. So today I'm going to talk about one of my PhD projects that I have done throughout my PhD studies to utilize the urban overheating mitigation strategies to reduce urban heat stress and improve equity. So first of all, we know that actually heat can be doing a lot of damage on human health, such as doing dehydration to human health, and also doing heat strokes, heat cramps. But actually, surprisingly, that heat waves actually is the most deadliest natural disaster to the United States. And you can see that from the report from the National Weather Service, that heat waves is actually can do about 150 deaths per year in the US. And you can see this is actually not only a single case study in 2022, it actually has a 30-year average also attaining this high fatalities. And in our climate change world, we know that we are going to bring more frequent and more intense heat waves. The reason is because climate change is going to shift our weather to a warmer climate, and then to the same threshold that we are going to experience more hot weather. And at the same time, we may even record more new hot weather and more extreme events. And this is not only a theory. From observation, we're already seeing that they are experiencing more heat wave events. And together with the increasing population, there are actually more population exposed to this type of heat wave events. And if you recall what happened in the summer in 2023, you can see that in a lot of big cities, such as Houston and Miami, we also record the hottest month in our summer in 2023. So that means that climate change bringing more frequent heat wave and intense heat wave is already occurring and is already been observed. And as we know that a lot of population, more than 60% of the population, close to 60% of the global population is actually residing on urban areas. So that's why we actually try to focus on heat waves, what is happening in urban areas. So one of the phenomena that we shouldn't be overlooked is the urban heat island effect. The urban heat island effect is the phenomenon denoted by the warmer urban centers compared with the surrounding rural area. It usually can reach up to about 2 to 5 degrees Celsius warmer compared to surrounding areas. And such phenomenon, urban heat island, actually can attribute by different factors. The first one is about the urban geometry and materials that can trap the solar radiation and the long wave radiation that will maintain a lot of energy inside the urban canyons to heat up the urban canyons. The second factor is the anthropogenic heat flux. These are the heat flux that due to human activities such as buildings, vehicles, or even human metabolisms that actually provide extra heat sources to the urban areas that can further warm up the urban areas compared to surrounding rural areas. And the third one is about the concrete land surface, or you can see that there are limited vegetation in urban areas. So this actually inhibit the evapotranspiration and lower the moisture availability. So that will partition more energy into the sensible heat flux, which is more related with heat compared with the latent heat flux. And a lot of studies already showing that the urban heat island effect can actually exacerbate heat wave and cause urban overheating. Urban overheating is defined as urban heating in the heating in the urban environment that can cause damage to human health. So urban heat island effect, urban heat island intensity often defined as the temperature difference between the urban center and the surrounding rural area. So exacerbating heat wave means that such the temperature difference between the urban center and the surrounding rural area, it actually can be increased during urban heat waves. So that means if a heat wave is going to hit an urban area, the temperature will be increasing much more than the normal conditions. So together with the climate change that we have been observing, the compound effects with the climate change and urban heat islands is going to further exacerbate the heat wave in the future. So that's what we are going to consider a lot. We're going to focus on looking at the heat waves happens in the urban areas. And we know that actually heat waves actually doesn't only impact the doesn't impact the urban area uniformly. We actually see some disproportionate impact from heat. So the disproportionate impact actually impact on the vulnerable groups differently, can through different pathways. The first one is the physiological pathways, such as children, elderly, and people with chronic disease. they're more sensitive to the heat stress because their body going to have some species react to the heat, the temperature changes. And the second pathway is actually through the social pathway, which is the neighborhood design or the urban design. So we can see that from a lot of studies, from the GIS studies, we've seen that the urban design, we see some of neighborhoods, such as the low-income neighborhoods, actually usually designed to be having a much less vegetation coverage. For less vegetation coverage, they're actually usually for the neighborhoods that we are seeing that is higher heat stress to be a warmer neighborhood in the urban areas. So to quantify such disproportionate impact, we can use an index called the Social Vulnerability Index. So this index is actually available in the US. They're going to rank each census tract in the US cities, ranking them from 0 to 1, with 1 to be the most vulnerable census tract. And they're ranking this based on 4 different criteria: the socioeconomic status, household composition, minority status, and housing type. And this social vulnerability index already showing that they're actually having some impact. They're actually having some relationship with the emergency medical service. And from one of the studies that done in San Antonio heat waves, they found that the emergency medical service is actually significantly related to the SVI during heat wave events. That means they're actually seeing more emergency medical service required by the vulnerable neighborhoods in San Antonio during the heat waves happened in 2018. So one of the questions that raised here that can we actually mitigate the urban overheating by considering the equity into our consideration by creating stronger cooling in those vulnerable neighborhoods? So that's actually how this project actually raised up. So some of the urban overheating mitigation strategies I have considered in my study is the cool roof. The cool roof is trying to paint the rooftop with high albedo substances or paint that's going to reflect the sunlight from the urban canyons and going back to the outer space to reduce the energy input to the urban canyons and cool down the urban canyons. The green roofs, they're trying to plant vegetation on top of the roof that can promote evapotranspiration to cool down the urban canyons. The urban trees is trying to plant trees along the streets. It can also promote cooling by enhancing evapotranspiration and also provide shading to the pedestrian. So the methodology I use here, I'm using a numerical methods. I'm trying to identify some of the heat wave events that happens in Houston area and trying to do the model simulation with modifying the urban models to incorporate urban trees impact and trying to do some model modification to incorporate urban variability that I'm going to introduce more in the later part of my presentation. And then I'm going to do 4 experiments. The one of them is the control experiment, and the 3 of them are different mitigation strategies. And finally, I'm going to compare the thermal comfort changes from these mitigation strategies and trying to compare that with the equity. So first of all, I'm going to talk about how do I identify the heat wave cases. We have selected Houston as our testbed due to his strong urban heat island effect actually been observed from different observations. And also because of his, due to his high population density, Houston is actually the 4th most populous cities in the US. So that's why we select Houston to be our testbed. And we have taken a look what are the station data around around the Houston area. And we found that there are actually 5 of the stations have run more than 30 years, from 1990 to 2019. So we use 30 years because 30 years usually we define as the climatology. So we use these 5 stations to define the climatology for Houston. And we take a look at the daily maximum for each of the day throughout these 30 years in Houston area. And we take a look at the daily maximum and take a look at the summer area, summer region from June, July to August. And we identify this region to be our threshold. We take an average of June, July, and August and set up the threshold to be 32.1 degrees Celsius to be the threshold for identifying heat waves that happen in Houston area. And then we use the duration for longer 14 days because we know that heat waves has to be long in order to give a prolonged effect on human health. So we define 14 days to be our threshold to be identifying the heat wave events happens in Houston. And we have identified 5 hottest cases to be the simulation, to be the cases that we're going to simulate in our later simulations. So after, and I'm going to introduce the model setup that we have done here. We are using a mesoscale model called a weather research and forecasting model. We use the version 4.4 because it has the capability to incorporate more urban intra-variability. So this is the model that often used in the weather research community that is widely used and widely is maintained by the community and also from the university. And we have used a free domain nesting so that we are going to have a 9 kilometer and all the way to 1 kilometer in the innermost domain to be our simulation, to be simulating of our heat waves events in Houston area. And we're using the error 5 as our boundary conditions to drive the model. As I mentioned that I have identified 5 hottest heat wave events happens in 2017 to 2019. So we're going to take ensemble the average of these 5 heat wave events to evaluate the results. And I have used the urban model called the BAP-BAM model, the building energy model, and the building parameterization. So this is actually a multi-layer urban canopy model to capture the urban feedbacks and urban processes that happen in a mesoscale model. And we have slightly modified this model to incorporate the urban trees effect that I'm going to introduce more in the later part. And we also enhanced the model to capture the intra-urban variability because we know that in urban areas, actually there are a lot of variability. For example, you know that if you're close to the main street, we always experience a much warmer temperature comparing with you getting more closer to the residential area. So we try to enhance the model, trying to capture this type of variability. So first of all, I'm going to talk about how do we modify our urban canopy model to incorporate the urban trees effect, because of the urban canopy model has already have the capability to incorporate the green roof and cool roof that I don't have to do the modification, but urban trees has not been implemented yet. So first of all, let's talk about what is the BAP-BAM model. So these are the 3 types of the model, urban canopy model that often used in mesoscale model or even global model. The SLAB model is the most simplest model. They have the surface energy balance equation and also have the surface layer scheme to estimate the surface fluxes from the urban surface back to the atmosphere. However, the SLAB model actually just assuming the land surface to be flat. So that actually does not consider the urban geometries. So that's why it advanced into another more advanced model called a single layer urban canopy model. The single layer urban canopy model is trying to accommodate the urban geometries by taking a look at the urban height, the building height, and the building orientation, such as we can take a look at the street orientations. So that can actually accommodate the shadow effects because they can calculate the radiation going to trap, how much radiation is going to trap inside the urban canyons by calculating, by estimating height and orientation, and also the zenith angle, which is the sunshine shining on into the urban canyons. To calculate how much reflection and how much radiation is going to trap inside the urban canyons in order to calculate the urban temperature much more accurately. And the multi-layer urban canopy model, this is the BAP-BAM model, what the BAP-BAM model does. It actually tries to even resolve the vertical distribution inside the urban canyons. So it actually try to calculate the fluxes, the momentum fluxes and energy fluxes between the surface of the buildings and into the urban canyons in different levels. However, you found that actually none of this model has considered the effect of trees. So that's what we did the modification in this BAP-BAM model to accommodate the urban tree shading effects. The idea for urban tree shading effect actually comes from the BAP-tree model. So this is the model that based on the BAP-BAM model to advance the model to accommodate tree effects. But this model actually has not been implemented into the WRF model yet because of the high computational required. So that's why I'm just taking a part of this BAP-tree model to accommodate the urban tree shading effects that has come from the idea from Dr. Scott Kringhoff and Dr. Alberto Martini. They are also my co-authors in this paper. So first of all, we take a look the trees here. We are going to accommodate tree effect by using the Beer's law. So the incoming solar radiation is going to intercept by the trees through the leaves and the branches. We use the Beer's law going to going to scale with the leaf area index of each trees, and also the clumping coefficient, which is like the shading going to provided by the trees. So we can calculate how much radiation is going to be trapped by the trees and how much radiation is going to reach on the ground. And we are going to scale that up with the tree canopy coverage with this TC. And you know that because not every areas in the urban grid is going to cover up by trees. Some of the areas is actually not covered by trees. So we actually calculate the other part that's 1 minus TC, the tree canopy coverage, to be the amount of radiation that can directly shine on the ground surface. So subtracting that, we can get the energy loss that can actually trap by the tree canopies. This through the leaves, the LAI, the leaf area index. And all of this energy loss that is trapped by trees is going to partition either to be sensible heat flux and latent heat flux. And we use a ratio called the Bowen ratio. Bowen ratio is going to tell you how much energy partition between the sensible heat flux and latent heat flux. So this is the simple way that we try to accommodate the shading effect from trees and going to see how much energy is going to intercept and going to reflect back to the, going to emit back to the atmosphere. And the second thing we have modified for the model is to capture the urban intra-urban variability. The first thing we have done here is trying to subcategorize the urban areas into more urban classes. So first of all, you can take a look here on the left-hand side, you can see this figure. The Google Earth image show you what is happening in Houston area. You can see there are some main street, there are some residential area, and you can see there are actually very different landscape. You can see along the main street, there are not a lot of vegetation coverage because there are a lot of streets, a lot of roads. And you can see in the residential area, there are much more trees. But if you see that in most of the mesoscale and the global scale modeling, we actually just use a single class to classify those all urban areas. So you can immediately imagine that, for example, in this residential area, we are kind of overestimating. There are much more urban concrete surface area. So that's why we use this local climate zones. The idea is actually given by Stewart and Oak in 2012. They try to subcategorize urban into finer classes, into 10 different classes, based on the morphology, such as the building height and the building spread, how the sparseness between the buildings. And also they also consider the perviousness coverage, which means how much vegetation on the land surface. So we are using these local climate zones to further subcategorize the urban classes, and we implemented this into our WRF model. And actually, recently, the first global local climate zones map already been released, and trying to use this in mesoscale model in the WRF community. However, we found that this actually may not be enough because the global map actually try to capture all the features around the globe, and we know that each city actually have very different characteristics. But that's why we try to generate our own local climate zone map, particularly for this purpose. And also we know that the local climate zone maps should be always constantly updated because we know the urban constantly expanding, and we know that a year between 5 years, an urban can extend for more than 10 kilometers, 10 squares of kilometers. So that's why we also generate our own local climate zone map for Houston area. The way we do that is we take in the Landsat 8 imageries to be our input data, and we also define some training polygons on Google Earth. So we draw some polygons on Google Earth to tell the model that, so which region are going to be the residential area, the low-rise building, high-rise building, where are the compact buildings. And we're going to pass both information into a machine learning model. We use the random forest model, and we will generate the local climate zone map. And this process has to be gone through a few cycles, because we have to further evaluate and further improve the training by drawing more polygons in order to confirm that we are going to supply enough data into the machine learning model to get an accurate results. And for local climate zones, it actually has some default parameters that's given by the community. So you can see this is a general parameters that given by the community that for the open low rise, usually characterizing the residential area. and the large low-rise are usually the big buildings along the main streets, such as the big supermarket like Walmart. So you can see these two different classes already have a very big difference. For example, you can see from the pervious coverage, which means the vegetation coverage for the large low-rise has about 0 to 20%. But the open low-rise, such as residential area, can reach up to 30 to 60%. And we're using these parameters to passing this into our WRF simulation to take a look, how can this improve our simulation for the temperature that we're simulating for heat wave events. We compare the simulated land surface temperature with the observation. We use the MODIS observations. And in order to better compare the spatial pattern of the land surface temperature, we use a method called the scale land surface temperature method. We try to scale the land surface temperature method by subtracting the land surface temperature with the mean inside the urban area and divided by the standard deviation in the urban areas, so that we can enhance the spatial differences in our visualizations. So you can see that in the observations, you see there is a you can see the region along the main street, along the main highways, they are usually warmer. And you can also see there are warmer center in the urban center. And you can see if we're using the local climate zones, you can actually capture this warmer street features compared with our originally, we used the one single class classifications. We couldn't capture these street features. However, you can see that the local climate zone actually couldn't help us to capture the warmer urban center as well. But at least the local climate zone can give us some improvement to capture the intra-urban variability by capturing such warmer street features. And why a local climate zone can help us to capture this? We can take a look what is actually happening along the main street and comparing the main street with the surrounding residential area for a simple comparison. You can see that along the main street, we are experiencing a warmer temperature. And we can take a look what is happening for the energy balance equation. The energy balance equation showing that the incoming net shortwave radiation, which is the orange line, and the net longwave radiation, which is the light blue line, it also showed not a big difference. Sorry, I have to say that this solid line are the main street and the dotted line are the residential area. So we can see that both lines actually quite overlap each other. The only difference is actually happens in the sensible heat flux and the latent heat flux. And we see that because the energy input into the urban canyons for both residential area and the main street are pretty similar. The only difference is actually the partition between the latent heat flux and the sensible heat flux. And we see that because the main street is actually having less vegetation. Less vegetation means that there are going to be less latent heat flux because there will be less evapotranspiration. But because we know that the input energy is going to be constant, so that means the energy, all of the energy will going back to the sensible heat flux. And sensible heat flux will be closely related to the temperature that we can measure in the urban canyons. And one more extra factors that because we know that the anthropogenic heat flux from the large low-rise, which is along the main street, is going to be higher comparing with the residential area, because you know that there are more cars along the main street, along the highways, they're going to emit more extra heat sources. And this is going to provide extra heat sources to further warm up the urban areas. So that's why we will see there are warmer streets comparing with the surrounding residential area. And this can be captured from the model. And the second thing we try to further enhance is we try to enhance the representation of urban morphology. The urban morphology means that is such as the building height or the footprint of the buildings, such as how much area is going to occupy by a building. And we're going to characterize the urban morphology grid by grid. We're using a data set called the UT Globus. The Globus is representing the global building height for urban studies. So this is a data set and a methodology developed from one of our teammates called Harsh Kamav in 2022. He's actually using the digital service model and the digital elevation model. The digital service model is actually space-borne spatial measurement trying to capture the surface of the elevation of the surface and on the Earth's surface. So you can see the digital surface model cannot penetrate the building height or the vegetations. So that the red line is showing you the digital surface model can capture the building height, and the digital elevation model, or we call it digital terrain model, is actually can penetrate those buildings and vegetations and get the topography height. So if you're subtracting both, you can get what is the height for the buildings. And we also use the population density and building footprint as input in order to get more morphology parameters. The building footprint is going to give you how much surface area is going to occupy by each buildings. And we have used the LiDAR data in US to be our validation point. So we use this, passing both of the data into the deep neural networks in order to generalize what is measured from the global. And this method is actually further enhanced by Harsh by trying to improve by instead of using digital surface model and digital elevation model, into using a space-bound LiDAR measurement called ISAT, because this is going to give a higher precision. And we are passing these morphological parameters into our urban models. And we see that actually can further enhance our performance in simulating both temporally and spatially. We evaluated the urban station, which are the red dots in the in the Houston area. And we see that the urban station, which is using the globus, which is using this blue line, it actually improved in both daytime and nighttime. Using globus comparing with using the local climate zones default parameters, we can actually reduce the root mean square error and as well as the mean bias for both daytime and nighttime. And we further take a look at the spatial pattern. We zoom into the urban areas and we take a look what is happening in the observation. As we know that the main street warmer and the warmer center in the warmer urban center, the main street warmer can be captured by local climate zones. But with the globus, we can further capture this warmer urban center. So that's why in our latest study, we actually use this local climate zone with globus to be capturing the intra-urban variability to simulate our heat wave events in order to get a better accuracies. And I'm going to go through how do we design our experiment. First of all, the control experiment, we're going to take the roof albedo based on observations, which is from the HLSL30, which is based on Landsat 8 measurements. And we use the tree coverage is based on the tree equity score, and that is actually further based on the Earth Define, which is a measurement which is tree measurement that is done in the US in a very high resolutions. And we know that because in Houston, there is not a lot of roofs have been implemented with green roof, so we put 0 as our control experiment for the green roof fractions. And for the cool roof experiment, we try to do 2 scenarios, the less extensive scenarios and the more extensive scenarios. And we perturb the roof albedo based on different guidelines. The low scenarios is based on the Houston guidelines because it has a lower values. The high values is based on the Austin reflective roof guidelines. And we also did the same thing for green roofs. We also based on different incentive strategies based on different cities from Austin or New York City. We take the higher values, 80% to be the extensive scenario, the 30%, the low coverage to be the less extensive scenario. And for urban trees, we use a much different method because we know that to plant more trees, it is difficult to quantify how much trees should be planted, or difficult to validate, or difficult to say how much trees are required to be planted. So we actually use a score called the tree equity score. The tree equity score actually have actually give us the coverage required for different census tract to be added in order to maintain an equitable environment for different cities around in the US. So we use the 50% of the required coverage to reach equity to be our low scenario. and 100% coverage required to reach equity to be our high scenario. So we can imagine that the 50% is actually more like the 50% survival rate from the vegetation planted to be our urban tree scenarios. And then for evaluating the thermal comfort, we actually, instead of using temperature or heat index, we are using an index called a Universal Thermal Climate Index. So this index actually can consider both temperature, humidity, wind speed, and radiation. So if you recall that the heat index often used in our operation agencies actually try to consider temperature and humidity because we know that sweating on human surface, on human skin actually related to the temperature and humidity. But if you also recall that the wind chill index is trying to accommodate temperature and wind speed, because we know that the wind is going to make us feel chilly. So we know that because we know that both temperature, humidity, and wind speed is going to affect how human skin feels. But we didn't have an index that trying to accommodate all of factors into accommodating the human comfort. So that's why I'm using this index, the Universal Thermal Climate Index, try to accommodate the temperature, humidity, and wind speed. And as well as it also have an extra effect is from radiation. So for radiation, you can imagine that if you are exposed under sunlight, you can actually feel your skin is burning because the radiation is actually shining on top of your skin. So this is how the radiation effect is tried to accommodate from the UTCI. And studies has been showing that using this UTCI index can be actually better simulate what is human body is feeling, is sensing comparing with the heat index and temperature to the ambient stimuli. And the UTCI involved we are implementing here is trying to use a 6th order approximation. That means we're going to take all of the four factors and go up to the 6th order. And this implementation has already been published in the WRF Comfort. That is based on version 4.3. But you can also extract the same code into the version 4.4 if you want. So this has already been published. If you are interested, you can take a look at this paper. And the thermal comfort improved from these strategies. We can take a look in this graph. In this graph, and I'm averaging all of the urban grids in the Houston area and calculating the UTCI changes comparing with the control experiment, which is close to our observations. So you can see the dotted line are the less extensive scenario. The solid line are the more extensive scenarios. You can see the solid lines is always going to down, going to create a stronger cooling compared with the less extensive scenarios. So, and you can see that the blue lines in daylight in the daytime cooling is actually the strongest. The blue line are the cool roof. The red line is the urban trees, and the green line is the green roof. So we can see that in the urban average, in the sense of urban average, the cool roof actually in our current setting, it actually create the strongest daytime cooling, and then following by the urban trees and the green roof. And for simplicity in my later part of my presentation, I'm going to just investigating the high scenarios for easier to understand between different strategies. And we know that in this urban average UTCI changes here, I just consider the changes from the cooling from the intensity, the changes from the intensity of UTCI. So that's why we further enhance the calculation method by taking a look both intensity and duration, because you know that prolonged heating is going to impact more on human health. So we use an index called, we develop an index called the average daily cumulative heat stress, try to accommodate both the intensity and duration, and we define this as the heat stress that a human perceive. We try to calculate this by define a threshold. We use 26 degrees Celsius because from the UTCI community that's stating that starting from 26 degrees Celsius from UTCI, a human body is starting to experience heat stress. So we define 26 degrees Celsius as our threshold, and we integrate all of the temperature, the delta temperature above this threshold from all of the simulation days and events. And we calculate the percentage change from this heat stress comparing with our control experiment to see how much heat stress is reduced by different strategies. And we see that there is a slightly change. Now, urban trees and cool roofs are actually having a pretty similar amount of reduction of heat stress, followed by the cool roof, followed by the green roofs. And we further take a look what is happening in the spatial sense. We see that because we have implemented cool roofs, green roofs, and urban trees in different areas and differently, because you know that from the building morphology, you can only implement rooftop strategies on top of roofs. So that means if you have a bigger footprint of buildings in those areas, we are going to experience stronger cooling for the cool roofs. So we can see that in different areas, you can see different hotspot or cool spot for different strategies. And we try to take a look, what is the relationship with the social vulnerability index? So you recall that the SVI is actually quantifying how vulnerable for each neighborhood. So you can see here, from the cool roofs, we can see the reduction of the heat stress is actually having less reduction, which means has less cooling if we are going to more vulnerable regions. So that means in more vulnerable regions, if we are implementing cool roofs uniformly in the Houston area, we actually experience less cooling for those vulnerable regions. So this is the same for the green roofs as well. You can see less cooling in the vulnerable regions. However, for the urban trees, it's a reverse order. You can see that we're actually creating stronger cooling for those vulnerable neighborhoods. So I'm trying to quantify, trying to numerically compare how much is actually causing, how equitable for different strategies, because you can see that in graphically, we can see that urban trees now is more equitable because it's going to create strong cooling in the vulnerable neighborhoods. But we want to develop an index that can quantify, quantitatively compare different strategies. So that's why I developed this index called, trying to multiply the heat stress changes with the SVI. So if you recall that the SVI is actually only ranging from 0 to 1, with 1 to be most vulnerable regions. And the delta percent of ADCH, which means the percentage change can be created by the strategies, but through cooling, can range from negative to positive numbers. With negative number means that it's reducing heat stress. So if you multiply both values together, you can actually get a sense that a negative number, a positive number is going to deteriorate the equity because positive number is increasing heat stress. If more positive number, that means that you're increasing heat stress for the more vulnerable neighborhoods. So if you multiply them together, more positive values means that they're going to deteriorate equity more. If you close to 0, it is either the region is close to 0, the vulnerability is close to 0. That means it's very, very sustainable, very, very invulnerable, or actually no impact from the UTCI, actually no cooling or warming from the strategies. So that's why if you're close to 0, that means there's no change in the equity. If you're getting more negative values, because negative values, the sign is actually coming from the reduced heat stress, so more negative values is going to be improving the equity. So I have multiplied the index, both index together, and get the map and try to evaluate an urban average. And we can see that now urban trees is actually to be the most equitable solutions because it's actually creating stronger cooling in the urban areas, in the vulnerable neighborhoods, and then followed by the cool roofs and the green roofs. And we try to further take a look why urban trees can be the most equitable solution in Houston area. So first of all, we can take a look, we can know that because both the rooftop strategies and the urban tree strategies, they actually try to engineer service differently. The rooftop strategies is trying to engineer the rooftop, and the urban street trees is trying to engineer the street. So you can see that from a single grid inside the model is going to separate the rooftop and street differently. So if you're going to see a more rooftop in one of the grid points, more rooftop areas in one of the grid point, then we will see less street area for one of the grid point because they are actually contradicting. They're actually competing spaces. So we can see that actually in Houston area, for vulnerable regions, high SPI regions, they're actually having more street fractions. That means they're actually having more spaces for us to plant trees. So therefore, we can actually have more added tree cover for those regions. So this is the reason why we're actually seeing urban trees can actually creating stronger cooling in the vulnerable regions in Houston area. But however, you can imagine that this can be varies by cities. So that's why the main ideas we want to bring here that if you want to design an equitable solution, you have to consider both the city morphology and also demographics. So in conclusion, that we can see that from a current study that cool roofs can be the most effective strategies in enhancing human comfort. If you remember that cool roofs can be creating the strongest daytime cooling if in an urban average, but it may not be the most equitable solutions. Urban trees are the most equitable solution in Houston by creating a stronger cooling in the vulnerable neighborhoods because they are having more street spaces for us to plant trees. However, that can be vary among cities. So one of the examples that I found from the literature is that in Arizona, Maricopa County, the uniform cool roof can actually yield more cooling in those vulnerable regions. So that's already an example showing you that in different cities in Arizona, Maricopa County, the cool roof may be a better strategies to be equitable solutions. So our study here is actually aimed to show the framework that to evaluate an equitable solution has to be considering both the morphology and the demographics. So last but not least, I would like to introduce some of the limitation or the future work from the current study that I have done here. One of the major limitations from the work I've done here that we're actually just incorporating the urban tree shading effects. So a lot of the effect from the evapotranspiration and the heat storage is actually ignored. So one of the literature actually showing that the heat storage from the trees or from the vegetation can actually even further enhance the nighttime temperature. So that's why if you are actually considering the vegetation implementation, vegetation mitigation strategies in urban areas, we also have to take a look what is happening for the nighttime, because it even can cause some nighttime warming if we're considering the vegetations. And in the intra-urban variability of the tree distribution currently now is limited by the LCC class. So if you remember that in our urban morphology, we try to characterize grid by grid. But in the tree coverage, tree distribution for now, we're actually limited by class. So for example, we only have 10 different classes among Houston area. We're limited by the distribution of the trees. We couldn't characterize the tree coverage grid by grid for now yet. So this can be a future enhancement from the model community. Try to see, for example, if we're going to build parks in the urban center, is this going to creating a stronger cooling or not? So this is one of the limitations that currently I cannot do it right now. And one of the future work can be done is that we can also take a look what is happening for solar panel and cool pavement. So the solar panels, why we take a look at solar panels that because in the Houston government, it actually released some of the incentive programs trying to ask Texans to install solar panels on top of the rooftop. And this is also one of the emerging area trying to take a look what solar panels going to impact in urban temperature, because solar panel can actually reduce the use of energy burning of fossil fuel. But at the same time, solar panels actually having a lower albedo because of the black surface. You can also absorb energy from the solar radiation that can actually warm up the urban area as well. And also one of the limitation that we couldn't accommodate now, but this is very difficult, right? Because we know that there are actually some very innovative engineering methods that has been developed, such as using tree walls or the vegetated walls, or even planting vegetation on different floors. So these are some of the creative mitigation strategies that the current model cannot be captured. So yeah, So I would like to acknowledge this project is actually funded by NASA Finance Project, the DOE, the DOE project, and also the travel of the presentation of this project is actually funded by the NOAA. So I would like to take questions right now. So thank you very much.